In this video, we will be looking at the natural logarithm ln. But before we get into that, we're going to do a little warm up on the derivative of e to the x, a little warm up on log properties that you've learned in the past in advanced functions, and then a little inverse. All right, let's start off by finding the derivative of x times e to the power of 3x. And feel free to pause the video and try them on your own before you come back to check. So when we're taking the derivative, this is a product rule. So the derivative of x is 1, and then that will get multiplied by the second function, plus the derivative of e to the power of 3x is a chain rule. So we write e to the power of 3x because the derivative of e to the x is itself. And then now we'll take the derivative of that exponent, which is 3, and then make sure you remember to write the original first function. I'm just going to rewrite this to make it look a little better, so I'm going to put the 3x out front. If I wanted to, I could also factor out an e to the power of 3x. I would only do this if it was tied to a solving question, but why not in this little warm-up? For the next one, we have a quotient rule. So we'll start with the derivative of the numerator. The derivative of e to the power of 2x is e to the power of 2x, and then multiply it by the derivative of the exponent. And now we'll copy paste the denominator minus the derivative of the denominator, which is actually the exact same thing because the derivative of 1 is 0, and then the derivative of e to the 2x is e to the 2x times 2, and then that'll get multiplied by the original numerator all over the denominator squared. Now, in terms of cleaning up, I'm just going to look at this as one unit and this as the other, and they both have e to the power of 2x and a 2 in common. Here's 1 and 1, here's 1 and 1. So I'm just going to factor it out. So 2e to the power of 2x. When I take it out from the first unit, I'm just left with 1 plus e to the 2x. When I take it out from the second, I'm left with negative e to the 2x. And now these cancel out, so we're just left with 1 in the bracket, which means our nice and cleaned up version of the derivative is 2 e to the power of 2x all over 1 plus e to the 2x all squared. Okay. In terms of restrictions on this, there's nothing that's going to make that denominator negative because it's a bracket to the power of 2. Even if it wasn't, if I was setting 1 plus e to the 2x equal to 0, when I bring the 1 over, it becomes negative, and an exponential function in that form will never be in the negative. So no restriction regardless. All right, let's move on to some log properties that we've seen in the past. And the first one is 5 to the power of log base 5 of 2. When the base of the exponent and the base of the log is the same, the answer is just the argument of the logarithm. For the next one, keep the 4. Log base 3 of 9. We're asking ourselves 3 to the power of what gives me 9? Because remember, the answer to a logarithm is the exponent, and that exponent is 2, and 4 times 2 is 8. For the next one, log base 2 of 1. Here we're asking ourselves 2 to the power of what gives me 1? Well, anything to the power of 0 gives us 1. So there we are. All right, and next, a little inverse warm-up for something familiar, to the function 2 to the power of x. Then we'll do the same idea for e to the power of x. So we're going to graph each exponential function. We're going to determine the equation of the inverse, and then we're going to graph the inverse as well before we head into that natural natural logarithm. So for 2 to the power of x, 2 to the power of 0 is 1, so 0, 1. 2 to the power of 1 is 2, so 1, 2. 2 to the power of 2 is 4, so 2, 4. And 2 to the power of 3 is 8, so 3, 8. 2 to the negative 1 is a half. And I think that's good enough. And here's y equals 2 to the power of x. And we have that asymptote at y equals 0. Okay, for the inverse, whenever we're finding an inverse, let's swap x and y. So x equals 2 to the power of y. And now isolate for y. This is an exponential form. I'm going to convert it into a logarithmic form. So the exponent, remember, is the answer to the logarithm. The base of the exponent is the base of the log. And then the x is the argument. There we are. And let's graph that inverse. Now I'm not going to graph it from the log. I mean, I definitely could, but since I have those nice exponential points, I'm just going to swap x and y and go from there. So the point negative 1 1/2 is 1/2 negative 1. The point 0, 1 becomes 1, 0. The point 1, 2 becomes 2, 1. 2, 4 becomes 4, 2. 3, 8 becomes 8, 3. Here we are. And the exponential had a horizontal asymptote. This logarithm has a vertical one at x equals 0. And there we are. Now we're going to do the same thing and see what does e to the power of x look like and what does its inverse look like and what's the equation. So e, remember, is 2.7 something. So e to the power of 0 is going to be 1. E to the power of 1 is 2.7 something. So I'll just estimate it here. And you know what? I'm just going to use those 2 points. That'll be enough to get the job done. Now for the inverse, just like before, I'm going to swap x and y, and now I'll convert this into logarithmic form. So the exponent is the answer to the log, the base remains the base, so log base e, and x is now the argument. Now when I swap my points, 0, 1 becomes 1, 0, 1, comma 2.7 becomes 2.7, comma 1. And there we go. We still have that same logarithmic shape. And what we just graphed here, log base e of x, is actually the natural logarithm. So the inverse of e to the power of x is the natural logarithm where e is the base. And instead of writing log base e, we can actually write ln e. So I can rewrite this. Sorry, not ln e, ln x. And there we are. So let's take a closer look at the natural logarithm. So the exponential function y equals e to the x is called the natural exponential function. Its inverse, y equals log base e of x, or y equals ln x, is called the natural logarithmic function. Now, all of the logarithm rules that you learned in advanced functions, you can use for ln, because ln is a logarithm. It's just the base is e. Okay, so first, just refresher, using our calculators for ln for log. So in our calculators, we will plug in ln of 4.7. If you've never used the ln button, find it and punch this in, and you should get approximately 1.548. Then log of 8.1, 0.908. And then log base 2 of 7 is approximately 2.807. Now, if you don't have the calculator that lets you change the base, remember the change of base formula, which says log, and pick whatever base you want, and we're just going to use a base 10 so our calculator can handle it. So log of the argument over log of the original base. That will accomplish the exact same thing. Now, some log properties, but applying them to the natural logarithm. E to the power of ln 4. Now remember, ln is just log base e. So when we see it like that, we see, oh, the two bases match of the exponent and of the log. So this is equal to 4. So here's the property, e to the power of ln x is just equal to x. Now, ln of e squared, remember again, ln is just log base e of e to the power 2. Again, my bases match. This is just equal to 2. Just like the log law that says log, let's say base b of b to the x is just equal to x. Okay. 3 times ln e, again, ln is log base e of e, where we're asking ourselves, e to the power of what gives me e? Well, that's just 1. So that's just 3 times 1. And ln e is equal to 1. And finally, ln 1, that's log base e of 1. You're asking yourself, e to the power of what is 1? Anything to the power of 0 is 1. So ln 1 is always 0. Now, if you forget a rule, or at the beginning you might feel uncomfortable using ln, you could always rewrite ln as log base e. Now for the next, we're going to write each expression as a single logarithm, and we'll state the overall restriction. So we're going to start off with a refresher on the different log properties. And one of them is if you have a coefficient, it can be brought up to the exponent of the argument. So I'm going to start off by writing this as ln of x plus 4 to the power of 2 minus ln, and I'm just going to factor this for later on, x plus 4, x minus 2. And then if we have the subtraction of two logs, we can just divide their arguments. Same thing applies for ln. And once I've combined my arguments, I see that a set of x plus 4s can cancel out, so that I have a nice simplified expression. Now for the restriction, I'm going to go to the original functions. For the original argument, we want x plus 4. Remember, an argument always has to be positive. So we want x plus 4 to be greater than 0. This is linear. So x plus 4 just has to be, x just has to be greater than negative 4. For the other argument, this is a quadratic, it's a parabola. So for this one, you could do a sign analysis, but I'm just going to do a little sketch. I can see from the factored form here that the zeros are 2 and negative 4. So if I draw my parabola, it's in the positive region here. So from negative infinity to negative 4, actually I've just changed the way I'm communicating. So for x is less than negative 4 and when x is greater than 2. And now I just want to look at the overlap between my two sets of restrictions, and that will be the overall winner. So I'm going to do a little number line with negative 4 and positive 2. And the first restriction said I had to be greater than negative 4. The second one said I had to be less than, so that's definitely out of the picture, or greater than 2. This is no good because it doesn't apply to both. This is no good because it doesn't apply to both. This is our happy spot. So the overall restriction is that x has to be greater than 2. Okay, so make sure if your argument is quadratic, you are drawing that little parabola. Let's look at the next one. We have ln of, and I'm just going to factor here, plus, I'm going to bring that exponent up. And when we have the addition of two logarithms, we can multiply the arguments so that we have x plus 2, x minus 2, and x plus 3 cubed. Clearly, nothing cancels out here. That's the simplified form. Now I just have to think about the restriction. So for the first argument, it's a parabola with the zeros at -2 and 2. It's opening up. So my restrictions are x can be less than -2 or x can be greater than 2 because that's where it's in the positive region. For the other one, x has to be greater than -3. For the overlap, I'm going to do my number line. So -3, -2, +2. The first restriction said be less than -2 or more than +2. The second restriction said be bigger than -3. And if I look, I see a nice overlap between -3 and -2 and from 2 to infinity. And those are our two overall restrictions. If you satisfy one of those, then you will be able to evaluate the logarithm. All right, let's move on to some solving. So as you can tell, none of this video is really about derivatives. It's just, it should have some familiarity to it since you've learned logarithms in the past. It's just now we're dealing with a very specific type of logarithm where the base is e. So if I want to solve ln x equals ln 9 minus ln 6, well, first of all, I can do a log property here, and my arguments, I'll just divide them. And now that I have ln equals ln, it's log with the base of e on both sides, we can just set the arguments equal to each other. And my restriction would have been that x has to be greater than 0, and that satisfies that. The next one is an exponential equation. So I am just going to bring the -3 over to the other side. 4 plus 3 is 7. And then from here, we can turn this into logarithmic form, or we could take the ln of both sides. It'll accomplish the same thing. I think I'm just going to convert this into logarithmic form. So I'm going to have log base e of 7 equals 1 plus 2x. Log base e can just be written as ln 7, and I'll bring the 1 over and then divide everything by 2. And there's the answer, which is approximately 0.47. So just a little exponential solving. For the next one, okay, I see a restriction here, x is greater than 4, x is greater than -1. So this is the restriction that wins. I'm going to unite the lns because they're subtraction, so I can write it as the division of the arguments. And now that I have ln equals ln, I can set the arguments equal to each other. And at this point, I will just cross multiply. So 6 times x, 6 times 1 equals x minus 4. And now we just have a linear equation, and we need to bring things over. And we get -2. Now, if we look at our restriction, this does not satisfy it, so there's actually no solution. So it is important that you are checking your restrictions, because sometimes you'll be able to solve the equation, but the answer doesn't actually work because there was no solution to that equation. All right, next one, I'll just make a note of my restrictions. X is greater than 3/2, x is greater than -4, And this one is a parabola, but if we just think about it, it doesn't matter what x value you plug in. X to the power of 2 is always positive. Times 2 is always positive. Add 11 to that, still positive. There is no way to make that argument negative. So this one can be anything. So in terms of the winning restriction, x is greater than 3 over 2. Now, I have the addition of the ln, so I'm going to multiply the two arguments. And now, once again, I have ln equals ln, so I'm going to set the arguments equal to each other. But while I'm doing that, I'm just going to expand and simplify the argument. So 2x squared plus 8x minus 3x, so that's plus 5x, minus 12 equals 2x squared plus 11. The 2x squares cancel out, and now we have 5x equals 23 when we bring that negative 12 over, and x equals 23 over 5, which is 4.6, which does satisfy our restriction. So that's great. So just a refresher on the different strategies we used to solve logarithmic equations. And finally, last one, if f of x is equal to e to the x and g of x is ln x, so the inverses of each other, then determine the composite function f of g of x and the composite function g of f of x. So f of g of x means g of x will be the inside function. So ln x will go inside e to the x. So instead of x, we're going to write ln x. And if I have e to the ln x, remember, ln is just log base e. The bases match. So this is actually just x. Let's do it the other way around. G of f of x. Now my inside function will be e to the x. So I'm going to write ln, and instead of x, I'll have e to the x. And this again, ln is log base e. The bases match. Thinking of log properties, this is equal to x as well. And that's actually a property. Whenever you're taking the composite function of a function and its inverse, it will always equal x. So just a fun little property. And there it is, your introduction to the natural logarithm ln. But really, it's the same log properties with just one specific base. And that base is Euler's number, which is e.